Hello friends, I am Dr. Sunita, Assistant Professor, Government NPG Science College, Raipur, and in this video we are going to discuss the Joule-Thomson effect. Joule-Thomson effect, which is an effect given after the name of the discoverer, Joule and Thomson. Now, what is the Joule-Thomson effect? The phenomena of change in temperature. The phenomena of change in temperature produced when a gas is made to expand adiabatically from a region of high pressure to a region of low pressure. So whatever the change in temperature produced when the gas expands under adiabatic condition from high pressure to low pressure is known as the Joule-Thomson effect. And this change in temperature, this cooling effect, the decrease in the temperature which we are getting due to this expansion, this cooling effect is due to the decrease in the kinetic energy. Decrease in the kinetic energy of the gaseous molecule. Because a part of the work is done, a part of the energy is used in overcoming the van der Waals forces of attraction that exist between molecules during expansion. So this cooling effect is due to this decrease in the kinetic energy which is used to overcome the van der Waals forces of attraction. Van der Waals forces of attraction. And this Joule-Thomson effect is very small when a gas approaches an ideal behavior. Ideal behavior means this effect is very small, and the reason is that we have the condition Q is equals to 0, adiabatic condition. Adiabatic condition also in ideal gases the van der Waals forces are negligible. Van der Waals forces are negligible, nearly 0. Okay. So when the Q is 0, van der Waals expansion is forces of attraction is 0. So literally there is no work done. There is no expenditure of energy in overcoming this force of attraction during expansion. Further, when an ideal gas expands in vacuum, under vacuum, there is no work done. So work done is 0, Q is 0. So change in internal energy automatically becomes 0 from the first law of thermodynamics. From the first law of thermodynamics. Thus, when an ideal gas undergoes expansion under adiabatic condition in vacuum, there is literally no change in the internal energy. That means the internal energy of a given quantity of an ideal gas under adiabatic condition in vacuum at constant temperature is independent of its volume. Internal energy is independent of volume. Now we come to the Joule-Thomson coefficient, and for this Joule-Thomson coefficient we have to set an experimental setup. Let us see what is this. So we come to Joule-Thomson, that was the effect. Now we come to coefficient. Now in this case the setup is like this, where we have this porous plug, this is a piston, okay, this is another piston, A is a tube, B is also a tube, this is A, this is P, this is G, this is P1, this is P2, this is V2, this is V1. Okay, now let us see what is this. Here we have a tube is made up of non-conducting material and is fitted with a porous plug G in the middle, and the two pistons A and B are on the sides. Okay, this is B and these are the pistons. The tube is thoroughly insulated to ensure the adiabatic condition. Adiabatic condition where no heat is allowed to enter or leave the system. So it is totally insulated. A volume V1 of the gas is enclosed between the piston A and the porous plug G. It is forced slowly through the porous plug by moving the piston A inwards and is allowed to expand to a volume V2 at a lower pressure P2 by moving the piston P outward. Okay, when this is moving inward, this is moving outward. So let us see what is the work done on the system at piston A is equals to P1 V1. Now work done by the system at piston A is equals to minus P2 V2. So the net work done is given by minus P2 V2 plus P1 V1. And the system is under adiabatic condition. That is, it will not absorb or leave the system. So the work is performed at the expense of internal energy. So we have this expression. Or if we substitute this by equation, this becomes equal to enthalpy H2 is equals to H1. That means change in enthalpy is 0, which is a very important thing. The adiabatic expansion of real gases occurs not with the constant internal energy but with constant enthalpy. Therefore, this process is known as isothalpic process because we have no change in the enthalpy of the system. So, which is very important. Sometimes the question comes, the Joule-Thompson coefficient, the adiabatic expansion of the real gas occurs with constant enthalpy, or what is isothalpic in reference to Joule-Thompson effect. Then we have to show this phenomena, this work done, and we have to lead the equation, come to the conclusion of the delta H. Now since H is a state function, so del H is a complete differential. Then taking H as a function of pressure and temperature, let us see what happens. So this is very important. Make sure the questions come from this here only. Now since del H is a state function, so taking H as a function of pressure and temperature, we have at constant temperature varying the pressure, and here we have varied the temperature keeping the pressure constant. Now we know that del H over del T at constant P is equals to Cp. This we know from our molar specific heat at constant pressure. So the equation becomes del P at constant T, yes, plus Cp dt. Substituted the value of Cp in place of del H over del T, we got this equation. Now We know that the process of adiabatic expansion of the gases is isothermal. We got this equation, del H over del P at T Cp dt is equals to 0. Simply in this equation we have substituted delta H as 0. This becomes minus del H. Simply rearranging the equation, we got this Cp. Where del T is the lowering in the temperature or the cooling effect. Assuming mu Jt, now this quantity is known as mu Jt, that is the Joule-Thomson coefficient. It is denoted by mu and Jt. Jt stands for Joule-Thomson and this is for the coefficient. Okay. Assuming mu Jt to be constant over a small pressure range, this equation can be written as minus delta H delta T is equals to minus del H over del P at constant temperature Cp. Taking this delta pressure on the right hand side, we have this equation for the cooling effect, which is the lowering in the temperature produced as a result of the energy required to overcome the van der Waals forces of attraction existing between the expanding gas. So this is very important. This is the Joule-Thomson coefficient. Now in our next lecture, we will see what is the Joule-Thomson coefficient for an ideal gas and for the real gas. Thank you once again.